Cool. So hello everyone, I'm Yuxin Chen, and I'm a third-year PhD student from UC Berkeley, and it's my great pleasure to present my current early-stage explorations on the word model predictions for visual model predictive control. I'll start with a very simple but important questions. What is a word model? According to Jensen Huang, a word model is generative AI systems that learn to represent and predict real-world dynamics using sensory data like text, images, videos, actions to simulate environments. In robotics, there's a growing trend showing the great potential to leverage word models as generalized dynamic models. Despite the progress, the development of word models is still in the early stages. For example, in the Cosmos word model report they recently released, they claim that the current word models, including ours, fall short as reliable simulators for physical world. In another report from 1X, they claim that the 1X word model currently struggles to model interactions with held-out objects not seen in the training data. So while the robotics research community often highlights the promising potential of using word models, they often overlook their poor generalizability when encountering out-of-distribution visual elements. And in fact, they're very fragile and brittle when encountering unseen objects. To illustrate this challenge, consider we have a robot to help us cook a meal, and try to pick a green pepper and put it to the cooking pan. In open world deployments, novel visual distractor, for example, we have the pressure cooker or the amazon box. It's kind of very common. Can be seen in the kitchen. So with visual distractors, the word model may predict trajectories that is unsafe to roll out or hallucinate inaccurate motions. These failures have very great impact on the word model-based planning tasks. Let's consider solving the same task, but with a naive sampling-based motion planning method. We have a human instructor provide a task descriptions and the robot-like actions proposed by the pre-limitation learning policy. And then we try to use the word model to verify the candidate action plans and make the corresponding decision, which is good, which is not. As previously mentioned, once we have the novel objects involved, word model prediction often degrade. For example, it can have distorting, disappearing, or warping naturally across different predictive frames. As a result, the downstream verifier often fails to detect a planned motion, whether it will collide or not with the pod. Ultimately, this will lead to the deployment time failures, and these failures cause a strong limitation of the current pipeline. And our key insight is that relying solely on a training time solution is insufficient. And to this end, we introduce Reimagination with observation intervention, or ReOI, which is a test time plugin strategy that improves word models predictions in open world settings with unexpected distractors. And the key idea is to bring the test time observation closer to the word model's training distribution. So given an initial observation and an action sequence, now the question is, how can we detect the visual distractors? Our key insight, and actually that's based on our observations, is that the visual distractors underrepresented in the training distribution often tend to exhibit physically implausible behavior in the word model rollouts. In these cases, we can leverage a VLM to identify such distractors by visual reasoning, and the VLM will flag those objects that are distorted dramatically. And then we can then localize them with the image secondation model, like the second entity, and then remove them with imaging painting. With this observation intervention process, the word model can then reimagine the action plan outcomes using the modified input observation and mitigate the hallucinations. So here's an example of the word model rollouts before and after the reimagination. However, since the distractors are impinted, they're no longer modeled in predictions. And how can we account for these impinted objects? And actually, it's a very challenging problem because we never know the dynamics of these unseen projects. But in most robotic scenarios, thankfully, especially in the home scenarios, like most of them are stationary. So to maintain visual consistency for planning and verifications, in our initial exploration, we just assume all the obstacles we encountered are stationary with fixed depth, and we can reinsert them into each predict frame based on the order of the depth. Specifically, for each predict frame, we separate the robots, the test relevant objects, and also the background into different layers, and we estimate each layer's depth, and then combine them from like in a back to front order. By doing this, we ensure the correct occlusion and visual coherence across the predict frames. And with all this reimagined action outcome, we can then use the same pipeline with the VLM to identify and reject plans as before. And to select the outcome that best align with the human intervention, user intention. And we have conducted real-world experiments with different random layouts in the kitchen environments. And we observed that unfamiliar distractors will cause off-the-shelf word model. In this case, we use the Dino word model. It will cause the Dino word model to hallucinate and erase the target objects from the prediction. And our method, RealEye, can effectively mitigate these issues, aligns visual predictions with the ground truth, and reject those unsafe actions. We use two classic metrics to evaluate the word model prediction quality. So we're on the left, we have the SSIM, where the higher SSIM indicates closer structural similarity. And on the right-hand side, we have the LPIPs, where the lower LPIPs indicates greater perceptual similarity. And our results demonstrate that our method have provide more accurate visual predictions and also mitigates hallucination. And in terms of task success rates, our method provides more efficient and safe visual planning that results in higher success rate and lower collision rate. While our initial exploration is effective, but our method still can be improved in many ways. So first, as we mentioned before, we assume the static distractors. In case of the dynamic distractors, we can apply something similar to like flow-based method for novel scene synthesis. And in terms of like if we have the visual occlusion, we can introduce multi-view sensory inputs. And there are also many ways for action selections. In this case, we only opt for the off-the-shelf data. There's other ways, plenty of ways to do that. Finally, here's some takeaways. Our initial exploration demonstrates that first, the word model remains brittle with novel visual distractors. Second, our method is robust to both in distribution and out of distribution of distractors. And third, as a test time plugging method, we can improve up to 300% of the success rate. And for more detail, please check our archive and have to talk in the poster session. Thank you.
Do you have any questions in the room?
Oh, yeah.
So you talked a little bit towards the end about these dynamics. Could you say a little bit more about that? How do you imagine implementing that? Do you think what kinds of scenarios do you think that would work in versus not?
Yeah, because like for the unseen dynamic models, like objects, we never know the dynamics. So potentially, we can use the pre-trained flow model to assume like some some common patterns like the obstacle may have to do that. Because like that is mostly for the insertion part, because we clip those objects out to the reimagination and put it back. So in terms of put it back, we do not know the dynamics of those objects, how it will move or not.
That's the also promise of world models, right? That they could eventually predict how.
Yes, but the observation is that if those objects is never encountered during the training process of the world model may not be able to correctly predict the dynamics of those objects.
Thank you. Okay, let's thank our speakers.